Good day everyone. We are here to present to you our design for our Capstone Project for bridge engineering. For the design of railings, we assume a uniformly distributed load of 0.8 kN per meter and a concentrated load of 50 kN. Then we computed for the factored moment, which is given by the formula mu is equal to 0.1 W Ls squared plus 0.5 PLS over 6 times C, where C is equal to 1 plus PH over 0.457 minus 33 over 18. With this formula, we computed for the value of C to be 1.1360 and mu of 8.5283 kN meter. Then we compared the steel ratio and the minimum and maximum steel ratio. But to compute for the raw mean, we have to solve first the MCR, which is given by the formula MCR is equal to 0.632 square root of FC prime IA over YT. And the minimum steel ratio is equal to 0.85 FC prime over Fy, quantity 1 minus square root of 1 minus 2 times 1.2 FCR over theta BD squared times 0.85 FC prime. The maximum steel ratio is equal to 0.85 of the balanced steel ratio, where the balanced steel ratio is 0.85 betas of 1 times Fy over Fc prime multiplied by 600 over 600 plus Fy. With the formulas given, we have gathered a data of MCR is equal to 3.8066, minimum steel ratio of 4.75 times 10 raised to negative 3, balanced steel ratio is equal to 0.03783, and the maximum steel ratio of 0.2837. Then, we have to compare the actual shear of 0.5 P over 3 and the shear strength provided by the concrete. Vc is equal to 0.16 theta square root of Fc prime RWD. With the formulas given, we got an adequate result of 16.3 kN of Vc and 8.33 kN of Vu. For the design of post, we assume the same value of concentrated and uniformly distributed load we used to design railings. Then, solve for mu, which we computed to be 22.5 kN meter. Then we compare the steel ratio, maximum steel ratio, and minimum steel ratio, assuming that the bar diameter is 16 mm, stirrup diameter is 10 mm, and a concrete cover of 40 mm. We use the equation mu is equal to phi rho BD squared Fy, quantity 1 minus 0.59 rho Fy over Fc prime to compute for the steel ratio, and it is valued at 0.01076. Same equation of MCR for railings to be 7.4348 kN meter and a minimum steel ratio of 0.003346. Balanced steel ratio of 0.0378 and maximum steel ratio of 0.0284. The area is then computed with the formula AS is equal to rho BD and is valued to be 516.48 mm squared and divided with the area of single 16 mm bar diameter to know the quantity of reinforcing steel bars to be used. Then, compare the actual shear versus the shear strength of concrete. Phi Vc is equal to 0.16 phi square root of Fc prime RWD, which we computed to be 22.55. To check for the spacing of stirrups, we use the formula AV Fy dV over Vu minus Phi Vc. The computed spacing is D10 mm spaced at 350 mm. For the design of sidewalks, we computed for the dead loads around the sidewalks, railings, and posts, where we use the concrete unit weight multiplied by its volume. Moment dead load is computed at 5.8731 kN meter, and the live load moment is computed with the equation 4.07 times 2 times 1 times 1.5 times 0.25. Moment live load is equal to 10.175. The impact is equal to 15.24 over 1.81 plus 88 is equal to 0.3908. And the factored moment mu is 1.3 multiplied by moment live load plus moment dead load. The factored moment is equal to 20.863 kilonewton meter. The same formula was used to compute for the MCR and the minimum steel ratio, and it is valued at 4.43.181 and 0.003446 respectively. Maximum steel ratio is computed with 0.75 times 0.85 times 0.85 Fc prime over Fy times 600 over 600 plus Fy. Maximum steel ratio is equal to 0.02887. For the shrinkage and temperature bars, raw temperature is equal to 0.002. AS is equal to 0.002 times 250 times 270. AS is equal to 675 mm squared. For the spacing, pi over 4 times 16 squared times 1000 divided by 675 is equal to 297.89. Therefore, use 275 mm spacing. And for the number of reinforcing steel bars, N is equal to 275 is equal to 1000 minus 2 times 40 minus 2 times 20 minus N over 16 over N minus 1. Then, we use 4d16 mm.
For the design of slab, the first step is to solve for the slab thickness. Our bridge span is equal to 15 meters. So the thickness that we will use using the formula 1.2 times S plus 3000 divided by 30 is equal to 720 millimeters. The second step is to solve for the live load equivalent strip for interior and edge. For interior single lane loaded, the E interior is equal to 5129 millimeters. For the multi-lane load, E interior is equal to 3606 millimeter. And for the edge strip, E edge is equal to 1800 millimeter. The third step is to solve for the dead load. For this slab, we got 16.95168 kilonewton per meter squared. For the future wearing, we got 1.655 kilonewton per meter squared. And for the concrete barrier, we got 5.6506 kilonewton meter squared. Fourth step is to solve for the live load moments. For moment due to design track, the loads are 145, 145, and 35 kilonewton. And then we solve for the reactions at each side. At left side or the RA, the reaction is equal to 194.033 kilonewton. For right side or the RB, the reaction is equal to 130.967 kilonewton. And then we solve for the moment, and we got 831.750 kilonewton meter. For moment due to design tandem, the loads are 2110 kilonewton. And then we solve again for the reaction at each side. For the left side or the RA is equal to 118.8 kilonewton. And for the right side or the RB is equal to 101.2 kilonewton. And then we solve for the moment, which is equal to 759 kilonewton meter. For moment due to lane load, the uniform load is equal to 9.3 kilonewton per meter. And then solve for the moment, which is equal to 261 kilonewton meter. The fifth step is to solve for the load factors and load combinations. For strength limit state load factors, we use 1.25 for weight of structure, 1.5 for weight of bearing surface, and 1.75 for live load. Then we solve for N, which is equal to 0.95. For interior strip moment, we use dynamic load factor equal to 0.33. Then we solve for the moment for lane load, which is equal to 72 kilonewton meter. For live load is equal to 379 kilonewton meter. For future wearing is equal to 46 kilonewton meter. And dead load is equal to 476 kilonewton meter. And then we solved for the factored moment, which is equal to 1263 kilonewton meter. For edge strip moment, the moment for lane load is equal to 87.1875 kilonewton meter. For live load is equal to 455.9299 kilonewton meter. For future wearing is equal to 14.226 kilonewton meter. For dead load is equal to 565.0566 kilonewton meter. And then we solve again for the factored moment, which is equal to 1449.260 kilonewton meter. The sixth step is the reinforcement design. For interior strip, we assume that the diameter of bars is 28 millimeters. Then the depth is equal to 678 meters. We solve for RU and we got 3.0531 Newton per millimeter. We solve for M, which is equal to 17.647. Then we solve for the rho, which is equal to 7.807 times 10 raised to negative 3. After that, we solve for the required area, which is equal to 5293.202 millimeters squared. And then we solve for the spacing, which is equal to 116.328. For the interior strip, we will use D28 mm spaced at 100 millimeter. For edge strip, we solve for the rho, which is equal to 9.068 times 10 raised to negative 3. After that, we solve for the area, which is equal to 6148.104 millimeters squared. And then we solve for the maximum spacing, which is equal to 100.153 millimeter. So for the edge strip, we will use D28 mm spaced at 100 millimeters. The seventh step is the reinforcement distribution. For the interior strip, the main reinforcement that we will use is D28 mm bar, and its area is equal to 6.1575 mm squared. For the required transverse reinforcement is equal to 0.87983. For the maximum spacing, we will use D20 mm, and the maximum spacing is equal to 357.0081. So we will use D20 mm spaced at 350 mm. For the edge strip, the main reinforcement that we will use is D28 mm bar, and its area is equal to 6.1575 mm squared. The required transverse reinforcement is equal to 0.87983, and for the maximum spacing is we will use D20 mm bars, and the maximum spacing is equal to 357.0081. So we will use D20 mm spaced at 350 mm. The last step is the shrinkage and temperature bars. We will use number 13 at 4050 mm. So the final design of this slab is we will use number 13 at 4050 mm, D28 mm at 100 millimeters, and D20 mm at 350 millimeters. For the design of the girder, we assume the dimension that B is equal to 800 mm and height is equal to 950 mm. Then we solve for the dead load. For slab, we got 29.0988 kilonewton per meter. For beam, we got 17.936 kilonewton per meter. For the weight of the dead load is equal to 47.0348 kilonewton, and the moment for the dead load is equal to 1322.85375 kilonewton meter. Next is the live load. For moment due to the design track, the loads are 145, 145, and 35 kilonewton. And then we solve for the reaction at each side. At left side or the RA, the reaction is equal to 194.033 kilonewton. At the right side or RB is equal to 130.967 kilonewton. And then we solve for the moment, which is equal to 831.75 kilonewton meter. For moment due to design tandem, the loads are 2, 1, 10 kilonewton. Then we solve for the reaction at each side. For the reaction at left side, or the RA, is equal to 118.8 kilonewton. And for the right side, or RB, is equal to 101.2 kilonewton. And then we solve for the moment live load, which is equal to 759 kilonewton meter. For moment due to lane load, the uniform load is equal to 9.3 kilonewton per meter. So now we can solve for the moment live load, which is equal to 261.563 kilonewton meter. After that, we can now solve for the factored moment, which is equal to 3336.7237 kilonewton meter. After solving the factored moment, we can now solve for the raw, which is equal to 0.6 Pmax. Pmax now is equal to 0.85 times 0.85 times 28 over 420 times 600 over 600 plus 420, which is equal to 0.0283. Now we can solve for the raw, which is equal to 0.017. After solving the raw, we can now solve for the depth, which is equal to 874.0782 millimeters. The actual is equal to 950 minus 50 minus 12 minus 28 over 2, which is equal to 874 millimeter. After that, we can now solve for the area, which is equal to 1188. We will use the 25 millimeter bar for the girder. So now we can solve for the number of bars, which is equal to 20 pieces. Then check for the spacing. After that, we solve for the AS, AC, C over DT, MN, and VMN to check if we can adapt the section. The new AS is equal to 12315.0432 mm squared. For A is equal to 271.655 mm and C is equal to 319.595. Next is to check for the phi if it is equal to 0.90. C over dt is equal to 0.3656, which is less than 0.375. So the phi that we will use is 0.90. For the nominal moment, we will use the formula 0.85 Fc prime times A times B times depth minus A over 2, which is equal to 3818.0574 kilonewton meter. To solve for the phi mn, just multiply mn to 0.90, which is equal to 3436.252 kilonewton meter, which is greater than the mn. So we can now adapt the section. For the final design of the girder, the base now is equal to 800 mm, the height is equal to 950 mm, and we will use 10D28 mm.
Next would be the design of the substructure. For the pier caps, the dead loads and the live loads would be multiplied by 1.2 and 1.6 respectively. By using the design track load, we would be able to compute the reaction RA by using summation of moment RB, which would be equal to 845.3665 kN. By adding all the forces along y direction, we would be able to compute for the reaction of B, which is equal to 744.4599 kN. We would now choose the larger value for RA, which would be 845.366 kN, and multiply it by 2, which should be equal to 1690.733 kN. We would now assume the number and the spacing of the girders, which would be 5 girders spaced at 2250 mm. We would also assume the number of the pier cups, which would be 700 mm by 950 mm. And then, we would place the computed value for 2RA to the point load of the beam, and compute the reaction at A, which would be equal to 45,246.873 kN. We can now compute for the maximum moment at midspan, which would be equal to 2,939.62511 kN. The D would be computed using equation mu is equal to phi rho b d squared times Fy 1 minus 0.59 rho Fy over Fc, which would be equal to 877.0657 millimeters. The D actual would be 880 millimeters, which is approximately equal to the D computed. Therefore, we would adopt the assumed section. We would now recalculate the value for rho, which would be equal to 0.014042. The AS would be equal to 8650.17579 millimeters squared. N would be equal to 8,650.1759 divided by pi over 4 times 36 squared, which would be equal to 9 pieces d 36 mm. The spacing required would be equal to 124 millimeter, which would be greater than dB, greater than 4/3 MSA, and greater than 25 millimeters. The final design for the column pier would be 700 by 950 mm with 9 pieces D36 mm reinforcing bars. For the column pier, PU is calculated as 5 times 1690.7 plus 15.694 times 10.5, which is equal to 8618.452 kN. By assuming the dimension of the column pier, which is 600 millimeters, you would be able to compute for the AST, which is equal to 14,090.81984 millimeters squared. To check if the section is adequate, the computed value must be greater than 0.01 Ag but less than 0.08 Ag. Therefore, we can conclude that 600 mm diameter column pier would be adequate. The final design would be 700 by 950 mm for the pier cup and 600 mm diameter for the pier column.
For the design foundation, we should first get the value of the total dead loads and total live loads. To solve for the total dead loads, we should first get the value of the dead loads of slab, beams, pier cups, and pier column. For the dead load of slab, it is equal to 23.6 times 10.5 times 7.5 is equal to 1,858.5 kilonewton. For the dead load of beam, it is equal to 23.6 times 0.8 times 0.95 times 7.5 times 5 is equal to 672.6 kilonewton. For the dead load of pier cup, it is equal to 23.6 times 0.7 times 0.95 times 10.5 is equal to 164.787 kilonewton. For the dead load of pier column, it is equal to 23.6 times pi over 4 times 0.6 squared times 5 is equal to 33.3637 kilonewton. So, to solve for the total dead loads, we should get the summation of the dead loads of slab, beam, pier cups, and pier column. So, it is equal to 2,729.2507 kilonewton. As for the live load, the total live load is equal to the design, track, and lane load. So, for the design track, it is equal to 145 kilonewton plus 145 kilonewton plus 35 kilonewton is equal to 325 kilonewton. For the lane load, it is equal to 9.3 kilonewton per meter times 15 is equal to 139.5 kilonewton. So, for the total live load, it is equal to 325 plus 139.5 is equal to 464.5 kilonewton. For the proportioning of the footing, to solve for B, we should equate the Q net to P over A. So, Q net is equal to 200 minus 1/2 times the quantity 23.6 plus 19 times 2, which is equal to 157.4 kilonewton per meter squared. So, now let's equate Q net to P over A. So, 157.4 is equal to 2,729.2507 plus 464.5 all over B squared. So, therefore, the value of B is 4.504 meters, approximately 4.6 meters. So now, let's go to the structural design, which is PU is equal to 1.2 times PD plus 1.6 times PI. So, PU is equal to 1.2 times 2,729.2507 plus 1.6 times 464.5, which gives us the value of PU, which is equal to 4,018.30084 kilonewton. Now, to solve for QU, it is equal to 4,018.30084 all over 4.6 squared, which is equal to 189.9007 kilonewton per meter. Now, let's go to the punching shear. So, A sub O is equal to pi over 4 times the quantity 0.6 plus D squared. B sub O is equal to pi over 4 times the quantity 0.6 plus D. So, VU2 is equal to PU minus QU A sub O. So, it is equal to 4,018.30084 minus 189.9007 times the quantity pi over 4 times 0.6 plus D squared. So, it is equal to negative 149.14771 D squared minus 178.9772 D plus 3964.6077. So now, VC2 is equal to phi Vn, which gives us this equation. VC2 is equal to 1/3 times 1 times the square root of 28 times pi times the quantity of 0.6 plus D times 1,000. So, VC2 is equal to 5,541.2486 D squared plus 3,324.749153D. So now, we should equate VU2 to VC2. So, negative 149.14771 D squared minus 178.9772 D plus 3,964.6077 is equal to 5,541.2486 D squared plus 3,324.7492 D will be simplified as 5,690.3963 D squared plus 3,503.7264 minus 3,964.6077 will be equal to 0. So, therefore, the value of D is equal to 0.5818 meters. So now, let's go to the beam shear. W squared is equal to pi over 4 times 0.6 squared, which gives us the value of W, which is 0.5317 meters. So, VUL is equal to QU times B times the quantity LL minus D. So, the value of VUL is equal to 189.9007 times 4.6 times the quantity of 2.0342 minus D, which gives us the value of VUL, which is negative 873.54322 D plus 1776.9616. So now let's equate VCL to phi Vn, which gives us the value of VCL, which is 0.75 times 0.17 times the square root of 28 times 4 times D times 1,000. So, the value of VCL is equal to 2,698.6663 D. So, now, we should equate VUL to VCL. So, it is equal to negative 873.54322 D plus 1776.9616 is equal to 2,698.6663 D, which gives us the value of D, which is 0.4974 meters. Therefore, use D is equal to 0.5818 meters. Now, let's compute for DC, which is equal to D plus 1/2 times 36 plus 75, which is equal to 581.8 plus 1/2 times 36 plus 75. So, therefore, DC is equal to 674.8, which is approximately 700 meters. Now, let's compute for D, which is equal to 700 minus 1 half times 36 minus 75, which is equal to 607 millimeters. So, Q is equal to 3,193.7507 all over 4.6 squared plus 23.6 times 0.7. So, it is equal to 167.4534 kPa. So, it is less than QA, so therefore it is safe. Phi mn is equal to phi rho bd squared Fy times the quantity 1 minus 0.59 rho Fy over Fc. So, which gives us this equation, 1807.3477 times 10 raised to 6 is equal to 0.9 times rho times 4600 times 607 squared times 420 times the quantity 1 minus 0.59 times rho times 420 over 28. So, the value of rho is equal to 2.8952 times 10 raised to negative 3. So, the 4/3 of rho is equal to 3.8603 times 10 raised to negative 3. So, rho mean is equal to 0.003333, which is less than 4/3 of rho. So, therefore, use the value of rho as 2.8952 times 10 raised to negative 3.
AS would now be equal to 2.8952 times 10 negative 3 times 4,600 times 607 equals to 8,084.1474 millimeters squared. The number of bars needed would be equal to 8 pieces D36 mm. The spacing required would be equal to 506.857, which is greater than dB for third MSA and 25 millimeters. The center-to-center spacing would now be equal to 542.857, which would be greater than 450 millimeters. Therefore, use D36 mm spaced at 450 mm OC. We would now compute the new value for N, which will be equal to 10 pieces. Therefore, we would provide 10 pieces D36 mm spaced at 450 mm on center on longitudinal and transverse direction.